since the time of Heisenberg in 1925, when he said that quantum mechanics cannot speak of the intrinsic properties of electrons. It cannot speak of the intrinsic trajectory of the electrons around the nucleus of the atom. It only speaks about what he called observable quantities, namely quantities that are relative to the measurement apparatus and to the act of measurement which is performed on it. It's less well known and, yes, it's less accepted nowadays, especially in the West, that quantum physics is also a theory with no view of the world. Many Western scientists are looking for a view of the world that could be adapted to quantum mechanics, which fits with quantum mechanics. And in fact, it turns out to be very difficult and generates a lot of paradoxes. So maybe the best way is to accept that quantum physics is a theory with no view of the world. I think these two negative features are quite in tune with the spirit of Madhyamika philosophy. So when we compare quantum physics and Madhyamika philosophy, so I wonder whether it works, yes? Ah, yes, okay, yes. Oh, thank you. When we compare the two things, quantum physics and Madhyamika philosophy, some people say that we are comparing two views of the world. But I think that, in fact, what we are comparing, more than two views of the world, is two criticisms of views of the world, two critiques of even metaphysics. In Madhyamika, we find, for instance, that emptiness is the relinquishing of all views, especially in this 13th Karika of Nagarjuna. In quantum physics, we find something very similar. If we read some stuff by Niels Bohr, Niels Bohr said that quantum mechanics is a mathematical symbolism intended to predict probabilistically the outcome of experiments. Therefore, quantum mechanics, according to him, is not a picture of the world out there independently of us. It's a symbolism which is meant to predict events which are relative to our actions, to our experimental attempts at measuring. Now, if we try to explain this famous statement by Nagarjuna that emptiness is the relinquishing of all views, we find especially the comment by Tsongkhapa, who roughly says that the idea that we have to reject all theses is to be understood as intending a rejection of inherent existence, not existence in general, of course, not nihilism, but only inherent existence. But of course, relational existence is something obvious and accepted. Heisenberg said something very similar in a book of 1955. He said that quantum theory is no longer an image of nature as it is in itself independently of us. It's rather to be conceived as an image of our relationship with nature. So here again we have the theme of relations and of dependent arising, which is introduced by both systems. So now, this kind of way of understanding quantum mechanics can help a lot to make clearer certain statements of quantum mechanics which have appeared paradoxical before. So much paradoxical that most physicists were puzzled by them. For instance, there is a famous saying by Niels Bohr that those who are not shocked by quantum theory cannot possibly have understood it. So that means that in order to catch what quantum physics is saying, you have to accept to be really stunned, to have all your views of nature and even of knowledge completely turned upside down. Really stunned, to have all your views of nature and even of knowledge completely turned upside down. Richard Feynman, the famous American physicist, said something very similar. He said, but even stronger, maybe even even shorter. Nobody understands quantum mechanics. And yet, Richard Feynman was one of the best quantum physicists in the history of human thought. So if he says that, that means that it's quite difficult. But now, maybe, says Niels Bohr, maybe the problem is that we have not clearly made our choice between modes of understanding. Maybe we can understand quantum physics in a completely new way, not precisely as a picture, an image of nature, but as Heisenberg would have said that, as an image of our relations with nature. So if we change completely the meaning of the word understanding, then we might well understand quantum mechanics in spite of what Feynman said. So you see that in recent times there have been a development of a new kind of understanding of the meaning of quantum mechanics as a no-view predictive formalism. Many scientists, many physicists, not all of them, certainly, there are many of them who Another sign are not states of objects. They are states of our incomplete knowledge about objects. Here again, you see incomplete knowledge about objects with many hyphens. That means that it's relational rather than absolute. Chris Fuchs, a very young physicist, American physicist who teaches in Boston, told something maybe even more radical. He said, quantum theory is not a theory of nature at all, whatever we mean by nature out there independently of us. It's just a calculus for gambling on agents' experiences. Namely, we have to gamble, we have to predict something about what will come next, when we make experiments, and quantum theory is a probabilistic theory which enables us to gamble about these future results. So as soon as we have accepted this new kind of understanding of quantum mechanics, then many so-called mysteries of the theory become clearer. For instance, you know, there is a famous mystery in quantum mechanics. It's the so-called collapse of the wave function. People think that we associate in quantum mechanics a certain wave function to each physical system, for instance, to an electron, to an atom, and so on. And that this wave function enables us to calculate the probability of a certain experimental outcome. Now, as soon as we have made a measurement, for instance, a measurement of the position, this wave function suddenly collapses. It became what is called a wave packet, very narrow, very little, very localized. Whereas at the beginning, the wave function was extended everywhere, in all the space. So how is it that suddenly a measurement changes everything and collapses a big wave which fills all space into a little point? How is it possible? It was a mystery. Now, if we accept that, in fact, this famous wave function or quantum state is, in fact, only a mathematical tool to predict probabilities, then the whole mystery disappears. Because it's obvious that when we know more about a system, we change our probabilities, because the probabilities are our valuations, you know. For instance, James Hartle said it's not surprising that after a measurement, the state must be changed just to be in accord with new information, because the state is nothing intrinsic. It's something relative to our knowledge. For instance, let's take the example of a coin. We play face or tail. We throw the coin into the box, and it falls on either face or tail. Before we know anything about the coin, before we have opened the box and seen in it what is the position of the coin, we have to ascribe the probability 1/2 to finding the coin on face or the coin on tail. But when we open the box, we see in the box, suddenly we see, for instance, that the coin is on face. And then we say, the next time we'll come and see in the box, we'll certainly find the coin on face. Therefore, the probability has jumped from 1/2 to 1. 1 means certainty. And it has jumped, it has collapsed, so to speak. But this is no real collapse, this is not intrinsic collapse. It's just a collapse of our knowledge. Now, it's, of course, the situation in quantum mechanics is slightly different to that, but not so much. The difference is that in that case of a coin, we ignore what is the true position of the coin. But in quantum mechanics, it's even more radical. The coin, the little coin, the electron, for instance, would have no intrinsic position by itself. And therefore, the position of the electron is not only unknown, it is undetermined. But apart from this detail, which is very important, the situation is the same between the coin and the electron. Now, let's do a test. If it's true, as you know, all these scientists said, that quantum theory is nothing more and nothing else than a way to gamble about the outcome of an interaction between us and these objects, therefore, this theory should apply to any kind of object, not only to electrons, provided these objects have the same characteristic of having no intrinsic properties, but only relational properties. And it's the case. The test is positive, because recently, in the last 10 years, quantum theory has been applied to many other fields than physics. For instance, it has been applied to predict human decisions and human perceptions. That seems quite strange, because you think, what is common between electrons and human beings, human minds, actually? The common point is that both, namely quarks or electrons and so on, and human minds on the other side, have a common feature. This common feature is to have no intrinsic feature, namely no intrinsic nature. You know, the reactions of an electron is dependent on the type of experiment you do. Sorry, yes, I have to change this. So it's the reaction of an electron is relative to the experiment you do. But also the reaction of a human being is relative to the question you ask. So let me take an example. In microphysics, it is said usually that an electron has a spin. But in fact, this property of having a spin is not an intrinsic property. You cannot say that the electron intrinsically rotates around itself to give the famous spin. The spin is relative to certain acts of measurement with certain kinds of apparatuses that are called Stern-Gerlach apparatuses, which use non-uniform magnetic field. So the spin arises only, especially the values of the projections of the spin on certain directions of space, arise only relative to those types of experimental apparatuses. When you ask questions to human beings about the meaning of words, something very similar occurs. For instance, let's take the very simple word in English, head. And let me ask the question, what does head means? If I say that without any context, you may give several replies. But if I impose a certain context of speech, you would you will be prone to give this or that answer. For instance, if I say, okay, now I have legs and arms and a chest. What is the meaning of head? Usually, many people say, oh, head, I know what you mean. It's just a part of our body, the upper part of our body. After that, what is the meaning of head? Head of a company. So in this case, the meaning of head is a leader. Or if I say, okay, I speak of sources, origins, and so on. So I change the context of speech. And in that case, you may be more inclined to answer, oh, I mean that head is inclined to answer, oh, I mean that head is probably meaning a beginning. So according to the context of speech, you change the answer you give to the question, what is the meaning of head? Now, if you count the answers, you will find that they are exactly predicted by quantum mechanics, or quantum theory, rather. So that means that quantum theory is much more general than physics. It is a general theory for any kind of relational features. Let me clarify now certain strange problems or paradoxes of quantum theory by way of this purely relational view of its status. For instance, you know that it has been very surprising to see that quantum objects such as electrons or atoms have sometimes wave-like features and sometimes corpuscle-like features. It was so surprising that Einstein, who discovered this duality, was completely stunned by it. He said, you know, he discovered that for photons. Actually, we say now photons, but we should rather say light at that time. So he knew that light, before his work, was considered as made of waves, electromagnetic waves. But he discovered that light also behaved as particles. He called these particles quanta of light, and thereafter it was called photons. He was so surprised by this duality that he said it's impossible, because you cannot associate an extended wave with a little thing which is completely localized. It's impossible. It sounds impossible. But he added, it's impossible, but God seems to have found a trick to associate the two. So he was completely stunned by that. So maybe you don't have to be so puzzled by that. If you accept that, in fact, there are neither intrinsic waves nor intrinsic particles, but only relational waves and relational particles. Yes. For instance, you know, we observe this kind of pattern, which is a diffraction pattern. We can also observe an interference pattern. And we say, usually, waves produce this kind of pattern. Since electrons also produce this kind of pattern, therefore they are waves. But I must warn you, this is not a correct reasoning in logic. The fact that waves produce this pattern doesn't mean that anything that produces this pattern is a wave. It would be true if no other explanations of this kind of diffraction or interference pattern explain the same patterns. But in fact, there are alternative explanations, and therefore it's not true that electrons are intrinsically a wave. The same reasoning can be made for corpuscle. It's not true that electrons are intrinsically corpuscle. Therefore, Bohr said that we don't have either corpuscles or waves, we have neither corpuscles nor waves, neither intrinsic corpuscles nor intrinsic waves, but we have corpuscle-like appearances and wave-like appearances, namely relational features, features that co-arise with certain experimental context in which they manifest. This is Bohr's view. This, at least Bohr's mode of thinking. Moreover, there is even a theorem, a very precise mathematical theorem, that shows that if you fabricate a theory that applies to phenomena that are relative to mutually exclusive apparatuses or experimental context, then you are bound to observe wave-like distributions of phenomena. So that means here again that you don't have intrinsically existing waves out there. You have phenomena, namely co-arising appearances that take a distribution which is very similar to waves. Okay, so now let's see that interference, this strange wave-like feature, also occurs in a completely different context. It occurs in human decisions, in the field of human decisions. That seems absolutely amazing, but it fits what I said before, that quantum physics can be applied to all sorts of situations, including to the case of human decisions. Let's take a very simple game in which, here again, you throw a coin and you play face or tail. And you gamble. And you are said, if the coin falls on head, you win 2,000 rupees. If the coin falls on tail, you lose 1,000 rupees. Okay, would you play this game? Many people say, yes, let's try to play the game. Then the coin is thrown and it falls on face. You have won 2,000 rupees. Would you play again? 70% of the people say, yes, I would play again because I want to win more. If the coin falls on tail, you have lost 1,000 rupees. And you are asked, would you play again? Most people here again say, yes, I want to play again because I want to win some money, even though I've lost some money now. Okay, that's perfect. Now, let's suppose you have another case in which you have thrown the coin, but you have left the box closed and you don't know the outcome of the game. What is your decision according to whether you will play again or not? In normal logic, you would expect that your decision will be the average of the two decisions. Maybe that there is only a 65% probability that you decide to play again. But it's not the case. It's not true. In fact, people decide only at 35% that they will play again. How can it be accounted for? The best account which has been given is by quantum theory, ascribing you not a state of uncertainty according to whether the coin is on face and the coin is on tail, but rather a state of complete superposition, which is much stronger than an uncertainty. And therefore, this accounts for a kind of destructive interference between the two options, between a yes and no. So you have exactly the same phenomenon of interference for the decisions of human beings as for the electrons, which is absolutely stunning. So what is, once again, the common point between human beings, human minds especially, and electrons? Only the feature of non-intrinsic determinations. Only this. which is on the other one false. If you remove